Hey, this is my cryptography and network security assignment for documentation. I decided to make a video report because it would be easier to explain over video than writing a document. So, to start off, we were given a program and we were supposed to, use a buffer overflow attack and get to the access granted code even when we give the wrong password as input. So to do this, I first set up a virtual machine on my home lab. So yeah, these are my specs of the home server, home lab server. It's a virtual machine running in a home server. I installed the latest Ubuntu LTS and it's running the 5.15 kernel. I've disabled ASLR for running the attack. So I've been running my assignments in tmux sessions. So let's attach to my first tmux session. So here, as you can see, we have our program. If we just see the program, this is the code that was given to us, and I compiled it using these flags, gcc hack this program 1.c with no stack protector and exec stack. So we don't need exec stack for the first assignment because we will just be changing the instruction pointer. So I will be demonstrating how I did the same. So now if we I also use the G3 flag. So if you check my history, hack this program, I have to hit grep. So yeah, this was the exact thing I used to compile. Yeah, initially I didn't use zexec because we didn't need it. Anyways, so now if we go into GDB, I will show you how I demonstrated it. So here's our program. If we hit disassemble main, we get our main program here with our memory addresses that the code is stored in. Similarly, we can assemble is password okay, and we will get the memory locations. The issue is these are offsets, and you'll get the right memory locations only after the first execution of our program. So let's go ahead and hit run. And of course, since I didn't provide an argument, it errored out. So now that is done, I will run it with the correct attack string. But before I do, I want to mention what I did. So basically the buffer overflow attack runs right here when we call our string copy, which overrides the location at which the instruction pointer of the previous main function call was saved. Once that's overwritten, we directly jump right here where where we call our put as access granted. So basically anywhere that we would usually not have access to run the code, that's the memory location. So now if I go ahead and do disassemble main, we have the right memory locations here. So to save some time, I already have the saved string here. I used Python to format my input. So I figured the overflow, my stack size to hit the overflow was around 20 bytes, and this was the memory location to jump to once it was done. So 63 is basically this is the memory location of 0x0000 followed by 554 times and then 5263, and I've put it in reverse order since it's little endian. That was one of the problems I faced. I'll come to more problems once I go further into the explanation. But yeah, so now if I run if I do run and copy this string that I have to give it, it's asking me if I have to run from beginning, and here as you can see we have our access granted. So how did I do this? I first kept printing memory locations. So I had a breakpoint at around this place, so right before the string compare. So I'll just show you how I did it quickly. I added a breakpoint there, and now if I rerun the program with the right arguments, so here we can see that strcmp is locked. So if I just run info frame, we can get the location at which our previous instruction pointer is saved. So it's RIP because it's a 64-bit system. I did not compile it for 32-bit. I decided to go ahead with 64-bit because that's more modern. So we can go ahead and examine the location at which RIP is saved by just running x/48x and the memory location. And yeah, before I go ahead, this is how I got the memory location. I first print the memory location of x/48x, which is 2d4, and turns out my RIP is at 2e8, so I have to fill A. So 41 is the hexadecimal representation of capital A, which is 65. If you convert 65 you get 41. So I filled all the memory locations with A, and here with the right memory location, which it has to jump back to give us access granted. So yeah, that's like a quick run through of what I did in the first part. It was fairly straightforward and simple. This we can also run using ./a.out. Once we figure the memory locations, you can just do that. Access granted. So there you go. So yeah, this bash warning was something I had to go through a little bit of trouble for my second and fourth bit. So now the next part was to launch a Unix shell. So here what I essentially did was give me a second, I'll just attach. Yeah, this is our program. So here what I essentially did was make our program jump back to the location of ARGV. Since we have only 12 bytes in password, we can't really fit our shell code that launches a shell in those 12 bits. A minimum shell code is around 27 bytes, and here we have only 12 bytes. So I had to figure the right memory location for ARGV and make the instruction pointer point to the memory location that is that is right after the buffer overflow plus our address plus starting address of ARGV. So this is exactly what I did. So turns out it was 31 memory locations. This was my address of ARGV of 1. I had to specifically take ARGV of 1 because that's where our shell code stays. So a little bit about what I did, some math, and also another issue with bash is it doesn't take these null characters, it just ignores them. So I had to switch my shell to ZSH, which is slightly less secure. It can be ZSH, it can be fish, any shell other than bash would probably work. So if we see our shell here, it's ZSH. So our GDB will also use ZSH. So to quickly demonstrate this was and also Python 3 has issues where it randomly inserts characters. Whenever I try to print FF, I get a random CA or AC. So here was the problem. that I faced, and this is the third problem that I mentioned. And also turns out the shellcode supplied in the PDF around here. Yeah, this shellcode didn't work. I think that's because it's for the 32-bit system. So I went to another resource provided in the my assignment PDF, and let me just quickly go to that. Yeah, this was the resource I used very heavily. It had a lot of links as well. So here they had the right shellcode. This was the shellcode that I ended up using in mine. Also, this video explained very well on how to execute buffer overflow attacks. Again, another issue is here the buffer size was 500. In most of the resources you will find the buffer size is 500. Basically, this password, or anything, people call it the buffer variable, they have a string length of 100, but since it was 12, that's what made the assignment a little more challenging. But it was simple. So the solution was pretty simple, since I had to fall back to ARGV of 1. So that was not a big issue. So I copy pasted this shellcode. And yeah, here as you can see, standard buffer overflow attacks, people put the shellcode first and then the overflow and then your address to that overflow. But what I had to do was I put the overflow first, then the right pointer right instruction memory location that would point to after all of this overflow, because we had to do the overflow in ARGV. So this was something unique that I think is not found anywhere online. So yeah, this is what I did. And yeah, even this resource was pretty helpful. I will come to that for the next part. So here, if we do gdb a2.o and hit run, as you can see, shell has opened. I can type commands ls cat hack test program.c, and yeah, it's a standard shell, it's working. And when I exit it, it also returns back normally. So that's a stealthy way of exiting from the buffer overflow attack. One tiny issue with this is, however, when I run the same with /a2.o, I don't get a shell. I can show the same with ZSH. So if I do /a2.o with this, it gives me a segmentation fault. I am yet to debug it further, but it works in GDB as I showed. Let me run that again. So if I do run and my string, we get our shell here. So yeah, that was assignment 2. Now coming to assignment 3, this was the part 4, which is posting system data periodically with using the right system calls, obviously. So this was challenging because I had to end up making my own shellcode. This is because there was no shellcode that would launch a Python script. So I essentially wanted to offload basically how we run bash from our C. I wanted to run a Python script from C, because Python is very simple in making posts, post requests, or anything you want to do. But turns out there was no pre-existing bash code. So in the same Talon website, they gave a reference to this shellstorm. I had to scour through the entire list of shellcodes that they already have. So if we go here, we can see they have a bunch of shellcodes, and our target is Linux, Intel x86 64, since I'm using a 64-bit OS. So they have a bunch of stuff. They also have a reverse shell and a lot of things, but there was no custom attack that I could launch. So I ended up writing my own assembly, compiling it and getting the binary. So I used this document, and I went through how they would open a shell. So here we can clearly see it's a very well written document. Here they're launching /bin/sh, which they converted to hex. So instead of calling /bin/bash, give me a second. Oh, sorry. tmux attach minus buffer attach. Yeah. Okay. So here, what I essentially did was made my own shell script called /bin/hack. So if I cat /bin/hack, it's a simple bash file that will launch a Python 3 script, and the Python 3 script is stored here. And if we cat this, it's a Python program. I will explain the Python program right after I execute my buffer overflow, the attack. So yeah, I ended up making my own shell script, which is right here. That took some time. I will explain the issues that I had to go through after I run this. So as you can see here, it says thanks got sys data. Now this sends information to my own cloud DigitalOcean server that's running in Bangalore. So if we attach it to our PWN server that's running in the background, here you can see we are getting every 10 seconds we get CPU information and memory information. We can get various other information such as the number of users logged in, all the users, basically any command you wish to run, since we're offloading it to Python. So yeah, this updates every 10 seconds. So you can see that it's 22 11 44 22, and then when it comes to 32 in the next 2 seconds, right, yeah, here you go. So we will keep getting our system data, and that is from running our program. Let me just run it from start and show you. So here we have our A3, so gdb a3.o, and if I do run this whole thing, let me run that again. There's some issue with that. So yeah, turns out there was a change in the memory address, which happens very frequently. I just had to debug and figure that out. So this is our new memory location, and yeah, this is where our shell code for /bin/hack would be. And yeah, as I mentioned, let me quickly run this again and show it to you. So it keeps saying thanks got sys data, and it sends it to a server, which I will show shortly. So if we go into the bash file /bin/hack, so it invokes a Python file that is in this directory. So let me quickly go there, and if we see the Python the Python script, so here we are running two commands, lscpu and free -h, and we are putting them in a simple JSON file, and we are posting that data to my personal cloud server in Bangalore, and this happens frequently at every 10 seconds. So yeah, here you can see it's happening. Now if we SSH into my cloud server, I will just show you the basic setup. So firstly, this route, this endpoint is fully secure, so you can open route.shrikar.tech, and yeah, that's just the basic route. It's fully secure, end-to-end protocol server. And how did I get this working? I to invoke the what do you say, the Python script. I was describing, I went through this. You can see my code here, cat temp.s. So this is the assembly that I wrote to invoke slash bin slash bash slash bin slash hack. And yeah, that's about it. It will keep posting system data, and we can see the data here. So yeah, here you can see every 10 seconds we get our system data. And this was pretty challenging because I tried using Metasploit to generate the code, but turns out it was only generating it for x86, which is the 32-bit system, and I needed x86 64. Hence I generated my own hex code, and yep, that marks the return to libc attack. So yeah, we've hijacked a remote machine, and it posts valuable information to my server that I have access to. So yeah, that should be about the data. Oh, I did an object dump too. I also used Python to calculate all the addresses, and I also can show you how I got the memory location. I did an object dump basically. So cd temp obj dump -o temp .o. Yeah, this is how I got my object code. So yep, that should mark the end of my presentation or project report. Hopefully it wasn't too long. Thank you and bye.